Okay, so what I want to do is go through this question, which is sort of a first question on the definition of convergence. So up here, I've reminded you what the definition of tending to zero is. We're going to need it sort of generally throughout the course, so you're going to have to imprint that on your mind. And let's just look at this specific question. We'll get to this towards the end. So part A, so this is the sequence we're looking at. Xn is 2 over n plus 3. And the question asks us to show that beyond the 100th term, all of the terms are within 1/50th of 0. So if n is bigger than 100, then we see that xn, or what is xn, is just 2 over n plus 3. So n is bigger than 100, so n plus 3 is bigger than 103, so this is less than 2 over 103. 2 over 103 is going to be less than 2 over 100, which is equal to 50. So if n is bigger than 100, then the nth term is less than a 50th, so we're done. So another way we could have done, or we could have shown, I won't go into the details here, we could have shown that x101 is less than 1 over 50. You can actually work that out, and then show that xn is decreasing. So that would have been another way to attack this. But this sort of gives you it all in one go. So either of those would have been fine. Okay, so the next part of the question, part B, asks us to find a term after which all of the terms are less than, let me just find the number here, the terms are all within 1/500th of 0. So in this part, we're asked to find some so let me just do some rough work here. So this is rough. We want to find an n such that if n is bigger than big N, then xn is less than 1 over 500. Okay. So this is the thing we want to satisfy. So here we take so we have xn is 2 over n plus 3, and we want this to be less than 1 over 500. So if we just rearrange that a little, we get 1,000 is less than n plus 3, so n is bigger than 997. So that's only if that's true, only if that's true. Okay, so this is going to be the number we want. If this is true, then we're going to satisfy this inequality. So this is the figure we have to use. So now let's do the proper work. So now we can sort of write it down. Take the 997. So if n is bigger than 997, then xn is going to be 2 over n plus 3. N is bigger than 997, so the denominator is bigger than 1,000, so that's going to be less than 2 over 1,000, which is 1 over 500. Okay, so there we found our answer. So part C is similar. You do exactly the same calculation, except we replace 500 by 10,000 in that case, and what we do is you'll find in that calculation that you get 1997. So if little n is bigger than 19997, then this is going to be less than 20,000, 2 over 20,000, which is less than 1 over 10,000, which is equal to 1 over 10,000. So on this one we just take that one. Okay. So that was part C. In part D, well, we need to do the same thing again. but we're not actually given the number. So part D, we're just given an epsilon. So part D, so we want, so let's do our rough work again. We want to find, so what's an n such that if epsilon is bigger than 0, we want xn to be less than epsilon. So we want 2 over n plus 3 to be less than epsilon. So we want n plus 3 to be bigger than 2 over epsilon. So we want n to be bigger than 2 over epsilon plus 3. So again, we've done our rough work. So this is the thing we want to carry. Not true, only if that was true, only if that was true. And now we need to work backwards. So now we can take that. So if n is bigger than 2 over epsilon plus 3, then x little n, 2 over n plus 3, is going to be less than, because little n is bigger than this thing, so the denominator is bigger, so the whole thing is less than 2 over epsilon plus, minus 3, sorry, I didn't mind. That should be a minus sign there. So if that's true, and here the minus 3 is cancelled, and then the 2's will cancel, and then so that's exactly epsilon. So this is why we sort of picked this value as we get that out. So anything bigger than 2 over epsilon plus 3 will do here. So now let's just turn this into a proof. So the proof, we've got to write it down to show that our sequence satisfies this definition. So this says, part E is going to be exactly the same, but we're just going to have to write it down slightly differently. So with part E, so the definition says that this property has to be true for every epsilon. So suppose I give you an epsilon. It could be any number in the world that's bigger than 0. So I have to find an n such as this property holds. So we've just discovered which n we want to take. So then take n to be an integer. So we want n to be bigger than 2 over epsilon minus 3. So this isn't necessarily an integer, but we usually want big N to be an integer. So, you can just take the next integer bigger than that if you want. Then take N, so we have to show that whenever now little n is bigger than big N, we've got that the modulus of xn, the absolute value of xn, is less than epsilon. So if n is bigger than big N, well, we need to show that xn is between minus epsilon and epsilon, but minus epsilon is less than 0, but we always know that this sequence is always bigger than 0, so we get xn is less than that, but xn is equal to, whoops, just out of time now, 2 over n plus 3, which we just put in our argument now, so this is going to be less than 2 over big N plus 3, which is equal to 2 over epsilon minus 3 plus 3, which is equal to epsilon. So what we've got is that minus epsilon is less than xn is less than epsilon. So xn, so squeeze it in here, thus which satisfies exactly the conditions of the definition, so xn tends to 0. I'll stop there.